So we're looking at the last little bit of information we need to know for this course before the end of the semester. We've been looking at areas under a curve bounded between a continuous curve and the x-axis. We saw the difference between net area and total area. Net area took the area above the curve and the x-axis, subtracted off the area below the curve and the x-axis. The total area, we had to look at where were sections that fell below the x-axis, and we had to look at that integral, and we would look at the absolute value. So now we're going to look at area bounded between two curves. But before we do that, let's just recall what we were doing. So we were using substitution with definite integrals. And this is where we had some integral where it was either hard or not possible to integrate without doing this substitution. And so what we did is we found some function, that inner function of the composite function. And we noticed that if that derivative of it canceled out some other value in our function, we would use that. So if this says if g prime is continuous on an interval AB and f is continuous on the range of g of x equals u, then we can just say that the integral of f of g of x times g prime of x dx is equal to, this right here is changing the bounds. So we looked at it two different ways where we changed our bounds of our definite integral before we integrated, or we integrated and rewrote what u was in terms of x and kept the original bounds. So this is equal to the integral of g of a to g of b f of u du. At the end of the last piece, I recall of our lecture on this information, it was helpful sometimes if we could tell if a function is even or odd. So recall if a function is even, and first of all, you could tell if a function is even if you plug in negative x wherever you see an x, and you get back your original function f of x. This is a function that is symmetrical across the y-axis. And so if that's the case, then we could look at just the integral from 0 to a. Let's say we wanted to find the integral from negative a to a of f of x dx, and it was an even function, then we could just look at, well, it's the same thing as 2 times looking at the integral from the lower bound 0 to a. If we have an odd function, that tells us that if we plug in negative x wherever we see an x in our original function, f of x, this is equal to negative of f of x. These functions are symmetrical across the origin. And so if we were looking at the same value on the left of the y-axis and the right of the y-axis, so we're looking at f as an odd function, and we're looking at the integral from negative a to a of f of x dx, this is equal to 0. So I kind of brought some pictures up to just verify. So this first image here is an image of an even function. So notice this area on the right from 0 to a is the same thing as the area on the left from 0 to a. And so we could just look at the integral from 0 to a and double that to get what that integral from negative a to a is. If we notice that it's an odd function and we're going from negative a to a, we could just show the function is odd and then just say, well, the integral is going to equal to 0. Because this area above the curve, recall, is positive value. And this area below this curve right here is the negative. It's negative of the area that we would get above the curve. And that's why we had to look at the absolute values of that when we were looking at total area. So they're basically subtracting each other off. Okay. So now we're going to jump in and we're going to look at area bounded between two curves. Okay, so let's say that let's say that this right here, this upper curve right here is f of x. And we wanted to find this area bounded between this curve and the lower one right in here, g of x. If that's the case, we want to find what this area in here is in red. If we just looked at the area that was bounded between y equals f of x and looking at integral from a to b, notice that's all above the x-axis. And so that would actually just give us this area in here. But we want the area between f of x and g of x. So if we subtracted off this area that we would get if we took the integral from a to b of g of x from the area of below the curve of f of x, we could get that area just bounded between the two curves. Okay. So in this image, it says let A be the area of the region between the curves y equals f of x and g of x over the interval AB. So in this picture, it's red. We're assuming, and we need to make sure when we're looking at this, that our function f of x is the bigger function. It's the one above the other one. So in this case, we're assuming f of x is bigger than or equal to g of x on AB. So if we wanted to do this, the area that's in red, this is equal to the integral from a to b of f of x dx minus the integral from a to b of g of x dx. But we could rewrite this as a single integral and just say, well, that's the same thing as the integral from a to b of f of x minus g of x d of x. It's easier if we do that subtraction of the two functions first before we go and integrate. Okay, so what I just said is the same thing right here. This is just taken out of your book and it's a little more concise mathematically. So it says if f and g are continuous functions, our function f of x and g of x is greater than or equal to g of x throughout the curve AB, then the area of the region between the curves y equals f of x and g of x from a to b is the integral f minus g from a to b. And this notation is written below on how to say that. Okay, so let's look at some examples. Okay, so for the first example, we have y is equal to x squared minus 2 and y is equal to 2. And we want to find that area enclosed by the lines and the curves given. So we actually need to know where these two intersect. So we know the bounds of our integration. It's also helpful that if we graph these functions. And so let's look at the graphs of those first. And so if we were going to graph, let me just give myself some points. If we were going to graph this y equals x squared minus 2, if I think about this as the graph of y equals x squared, that minus 2 is shifting that down 2 units. That means my vertex is going to be at negative 2, 0. I know that it's going to cross the x-axis about here, the square root of 2. Okay. So this is what our graph of y equals x squared minus 2 looks like. And then if we were just to graph y equals 2, that's just a horizontal line going through 2, y equals 2. So we want to know where are these two graphs intersecting. So in order to figure that out, we're going to set those two equations equal to each other. So we have a system of equations, y equals 2, y equals x squared minus 2. I'm going to use substitution method. I'm going to go in wherever I see a y in one function, I'm going to go in and plug in 2. So we get 2 is equal to this x squared minus 2. So it's a quadratic formula or a quadratic function. I could set this equal to 0 and solve, or I can use the square root method I noticed if I add 2 to both sides, I can use my square root method, take the square root of both sides. I get x is plus or minus 2. And so I know what these points are. This is negative 2, 2. And this is, 2, 2. I was just thinking that, notice that this is an even function. So I'm going to look at this integral here right now from negative 2 to 2. Notice that parabola is symmetrical across that y-axis. If we look at the upper bound of our function, the upper bound is our value of 2. So think of it as if you were to make your rectangles in here, which one is the height? The height is the top function. Okay, so we're looking at that top function, which is 2, minus the bottom function. And the bottom function in this case is x squared minus 2. So make sure if there's more than one term in that function, you put parentheses around it. And then we have the dx. So technically, again, we can use the fact that these are even. And I can show it mathematically that this is even. F of x equals x squared minus 2. If I look at f of negative x, and I plug in negative x wherever I see an x in that function, I can show that I get back my original function. And so if I square negative x, I get back positive x squared. And then I have minus 2. So this is even. And I also know that if I had g of x equals 2, this is also even. If I plug in negative x wherever I see an x, well, there's no x in there. I get back my original function of 2. So I could use that form knowing that this is the same thing as 2 times the integral from 0 to 2 of this. Let's just distribute that negative in here and combine like terms. So this would be 2 minus x squared plus 2. So we really have 4 minus x squared dx. Okay, so this one isn't too bad to find the antiderivative of. We can just go in. And so the antiderivative of 4 is just 4x minus the antiderivative of x squared is x cubed over 3. And we're evaluating this from 0 to 2. So we go in and we plug in our upper bound wherever we see our x value. So we have 2 all times 4 times 2 minus 2 cubed all over 3 minus our lower bound. But notice when we plug in 0 wherever we see an x, and the antiderivative is just 0. So simplifying inside the bracket, 2 times 4 is 8 minus 2 cubed, which is 8 all over 3. I'm just going to get a common denominator. So common denominator inside the bracket is 3. So 8 is the same thing as 24 thirds minus 8 thirds. So we'll bring down that 2. So 24 minus 8. So this is 16 thirds. And 2 times 16 thirds gives us back 32 thirds. Okay, so we found that area bounded between y equals 2 and y equals x squared minus 2. Okay, so in this next example, notice that they give us the picture of the area they want us to find. And so look at, first of all, from here, from 0 to 1, notice that our upper function is the function x, y equals x. And that lower function is that function in here, which is this y equals x squared over 4. So I'm going to have to break this up into a couple different integrals. So if I'm looking at the area of this first piece, this is equal to the area from 0 to 1. My upper function goes first, which is x, minus my lower function, which in this case is x squared over 4 dx. And so then I also want to add the area underneath the curve from 1 to 2. So looking at this area from 1 to 2. So notice in here, this is bounded between 1 and 2. Our upper curve is the line y equals 1. So we have 1 minus the lower curve, which again is x squared over 4 dx. So this total area, we're going to have to sum both of those up. So I'm just going to write that really quickly. If these were the same bounds, we could rewrite this as a single integral, but they're not the same bounds on our integral, so we cannot do that. Okay, so let's find the antiderivative of x minus x squared over 4. So the antiderivative of x is x squared over 2 minus the antiderivative of x squared over 4 is x cubed, all over 3 times 4, which is 12. We're evaluating this from 0 to 1. Plus, so now looking this at integral. So the antiderivative of x, I'm sorry, 1 is x, plus, and we just saw that, not plus, minus. We just saw that the antiderivative of x squared over 4 is x cubed, all over 12. And this one is evaluated from 1 to 2. So always plugging in the upper bound first. And so if we plug in 1 wherever we see an x in that antiderivative for that first integral, we're going to get 1 squared over 2, which is 1/2, minus 1 cubed over 12, which is 1/12. Minus, well, now when we plug in 0 wherever we see an x, we just get 0. So plus, so now we're going to plug in 2 wherever we see an x here. So plugging in 2 wherever we see an x, we get 2 minus 2 cubed, which is 8, all over 12. Minus, now when we plug in 1, wherever we see that x, we need parentheses around there. But we saw that before when we plugged in 1, I already did kind of the work right here. We had 1/2 minus 1/12. Actually, no, we don't. Don't listen to me. Sorry about that. When we plug in 1 for x there, we get 1 minus 1 cubed all over 12 is 1/12. Now listen to me. Okay. So we need to simplify this. I'm thinking let's just leave things and let's distribute this negative. I know we're going to need a common denominator. We have 12 in there already. Let's just make things as a denominator of 12. So this 1/2 is the same thing as 6/12 minus 1/12 plus 2 getting a denominator of 12 is 24 twelfths minus 8 twelfths minus distributing that negative. So we have minus 1, which is the same thing as 12 twelfths. And distributing the negative here, we have plus 1/12. Okay, so summing our things up, we have 6 minus 1 is 5, 5 plus 24 is 29, 29 minus 8 is 21, 21 minus 12 is 9, and 9 plus 1. So I think if I did everything right, this is 10 twelfths, which reduces down to 5/6.
Isn't it 24 over 12, not 24 over 2?
Oops, you're right. 24 over 12. Thank you. That didn't change anything when I sum my numerators. Right. Okay. So same type of example, it's given us the picture of the area, it wants us to find it. Find the area under the curves. Notice here we have two separate functions, just kind of like we had done before. We have to split this up into two separate integrals. And so we have to look at the integral from 0 to 1. Our upper function in this case, always take the top function, which is x squared, minus the bottom function. I technically don't have to write this bottom function. This bottom function is x equals 0, or I'm sorry, y equals 0. So this is minus 0 dx. And so remember, when we were looking at the area bounded between a curve and the x-axis, we didn't put that minus 0 there. Technically, it is there, but we don't have to write it. Plus, we want to look at the area from 1 to 2. So if we look at which curve is on top there, well, this says x plus y equals 2. I need to rewrite this in terms of y equals. So I can get that by subtracting x on both sides of the equation. So this is y is equal to 2 minus x. 2 minus x dx. Okay, so the antiderivative of x squared is x cubed over 3. We're evaluating this from 0 to 1. Plus the antiderivative of 2 is 2x. Minus the antiderivative of x is x squared over 2. We're evaluating this from 1 to 2. So let's go in for the first piece and plug in 1 wherever we see an x. So we get 1 cubed over 3, which is just 1/3, minus plugging in 0 wherever we see an x, we just get 0. Plus, now let's go in and plug in 2 wherever we see an x for that second integral antiderivative. So plugging in 2 wherever we see an x, we got that 2 times 2, which is 4, minus 2 squared, which is 4, divided by 2, so that's 2. Minus, we need parentheses there. Now plugging in 1 wherever we saw the x. So 2 times 1, which is 2, minus 1 squared over 2, which is 1/2. Okay, so I have 1/3 plus 4 minus 2. So we might as well just combine that. 4 minus 2 is just 2. So plus 2. But this is minus 2 plus 1/2. So notice our 2's cancel with one another, and we're just left with 1/3 plus 1/2. So common denominator, we would have 2/6 plus 3/6, which gives us back 5/6. Okay. We would have only had to have done one integral if we would have integrated this with respect to y instead of with respect to x. So let me just give you the following. So if we have two curves, if a region is bounded by curves are described by the function of y, the approximating rectangles are horizontal instead of vertical. And the basic formula has y in place of x. And so in this case, I'm not going to go through the detail of the horizontal rectangles, but we're basically looking at the bottom bound on our y-axis, which is c, to our upper bound on the y-axis, which is d. We want to look at the function that falls to the right. Our function that falls to the right first is this f of y value. So f of y minus the function that is on the left, g of y dy. So let's go look at that same example we just did, and let's rewrite our functions in terms of y instead of in terms of x, and use this. So in here, let's rewrite each of these functions. We have this function on the right that was x plus y equals 2, but we want this as x equals. And so we can rewrite this as x is equal to 2 minus y. Notice the y value that's on the bottom is 0. So we're going to integrate from 0, and the y value on the top of this area is 1. The function to the right is this 2 minus y. And then we're going to subtract off the function which is on the left. Well, this also is y in terms of x. We have y is equal to x squared. So we want to rewrite that in terms of x in terms of y. If I took the square root of both sides, this is x is equal to plus or minus the square root of y. But our value, notice, is positive, and so this is just positive root y for this piece. And so we're going to subtract off the square root of y, which we know will be easier to integrate if we rewrite it as y to the 1/2 power. So minus y to the 1/2 power dy. So technically, I don't need those parentheses in there. And so now let's go and take the antiderivative of that. And so the antiderivative of 2 is 2y minus the antiderivative of y, which is y squared over 2, minus the antiderivative of y to the 1/2. So adding 1 to my exponent, I get 3/2. If I divide by 3/2, that's the same thing as multiplying by 2/3. We're evaluating this from 0 to 1. So now we're going to go in here wherever we see a y, we're going to plug in 1 first. So we have 2 times 1, which is 2, minus 1 squared over 2, which is 1/2, minus 1 to the 3/2 power is 1, so that will be minus 2/3. And if we now go in and plug in 0 wherever we see the y, that would just be subtracting off 0. So let's get a common denominator, which would be 6. So we can rewrite 2 to have a denominator of 6, and that would be 12/6 minus 1/2 is the same thing as 6. I'm sorry, no. I'm thinking of 12 is the same thing as 3/6 minus 2/3, so that's 4/6. So 12 minus 3 is 9. 9 minus 4 is 5. So this equals 5, 6, which is the same thing we had gotten when we integrated it with respect to x. And so if we want, we can change things in terms of y and integrate with respect of y instead of x. And you guys are going to be doing that a lot next semester when you start getting these volumes and start spinning them around your x-axis or y-axis, these curves. Okay, so graphing y equals 2 sine of x. Well, we want to find the area bounded between the curve. Y equals 2 sine of x, y equals sine 2 of x between 0 and pi. And so let's graph these. Okay, so we have, let's do pi fourths, pi halves, 3 pi halves, and pi. So I know my sine function starts at the origin. This 2 in front of the sine. My period doesn't affect my period. It's just making that amplitude be 2 instead of 1.
Wait, wouldn't it be 3 pi fourths, not 3 pi halves?
Oops, you're right, 3 pi fourths, thank you. And so if we start now here at the origin, sine goes up. And so we're going to hit 2 at pi halves. At pi, we're going to come back down and hit it at 0. So that's this function. Y equals sine of 2x. This 2 in here, this is making my period. I think, let's look at the period. So normally the period is between the 0 and x. I'm sorry, 2 pi. And so if we divide everything through by 2, our period is now length of pi. So that's why I put these marks in here, because I like to divide it into 4 equal pieces. And so again, it starts at 0. It's going to go up and it's going to hit 1. It's going to come back down, hit pi halves. It's going to come back down at 3 pi fourths, it hit -1 and comes up. Okay. So I believe that, and I think that that's true. I believe that the upper curve is always y equals 2 sine of x. So we have our upper curve, which is this 2 sine of x, minus our lower curve, which is the sine 2 of x. And our bounds are between 0 and pi. Okay, so taking the antiderivative of sine of x, the antiderivative of sine of x is negative cosine of x. So this is -2 cosine of x minus, it's like I'm using u sub here. And so the derivative of sine of just sine of x, that's cosine negative of 2x. When I take the derivative, that would normally just put the 2 there, so I'm going to have to divide by that new 2. And this is from 0 to pi. So let's go in and we plug in pi wherever we see an x. And this is really, because a minus a negative is really plus. So I have -2 cosine of pi plus cosine of 2 pi over 2 minus -2 cosine of 0 plus cosine, well, 2 times 0 is 0 over 2. Cosine of pi is -1, so -2 times -1, that gives us 2. Plus cosine of 2 pi is 1, so 1 over 2, so that gives us 1/2. This is really going to be a plus 2 cosine of 0. Cosine of 0 is 1, so that's just 2. Minus, just removing the negative, cosine of 0 is 1 all over 2, so 1/2. So notice our 1/2s cancel, and we're just left with 2 plus 2, which gives us 4.